General specification for valves, Part 5. Ball valves. Ball valves used in oil and gas applications must be robustly constructed, fire-safe, and leak-tight under both static and dynamic conditions. All ball valves shall be either full-bore or reduced-bore as specified in the valve datasheet. Trunnion-mounted ball valves are mandatory for all sizes 8 inches and above in ASME Class 150, 2 inches and above in ASME Class 300 through 2500, and for all sizes under high-pressure ratings such as API 10,000. Bore dimensions for reduced bore valves shall conform to industry specifications to ensure consistent flow performance and minimal pressure drop. Ball valves must be designed for bidirectional flow unless specified otherwise. The ball shall be of solid, one-piece construction made from forged or cast materials. Welded or fabricated balls are strictly prohibited. The valve body shall preferably be of split body or end entry type. Top entry designs may be accepted if explicitly stated in the technical requirements. The use of multi-piece bodies must not compromise pressure boundary integrity or sealing performance. All soft-seated ball valves shall be certified fire-safe in accordance with API 607, API 6FA, or ISO 10497. Fire testing certificates must be provided with the bid and be less than 5 years old. Metal-seated ball valves must be inherently fire-safe and capable of maintaining seal integrity under fire exposure. Where required, fire testing of metal-seated valves shall follow similar protocols and demonstrate zero through leakage after exposure to flame. Ball valves in sizes 6 inch and above shall be provided with sealant injection fittings on both the stem and seats. These fittings shall be constructed from stainless steel and equipped with non-return valves, giant button heads, and protective caps. The sealant system must allow for in-service injection without the need to depressurize the valve. The purpose of this system is to mitigate leakage in emergency scenarios, though valves must not be shipped or pressure tested with sealant already injected. Metal-to-metal seated ball valves shall feature hard-facing materials such as tungsten carbide on the ball and seat surfaces. Matching surfaces must have differing hardness ratings to prevent galling. Inconel 625 or similar high-nickel alloys are preferred for the upper and lower trunnion bearings, especially in sour and corrosive surfaces. The valve torque calculations must account for the coefficient of friction associated with these materials, and supplier must demonstrate functional operability across the full pressure range. Spring materials for ball valves shall be corrosion resistant and maintain preload at all service temperatures. Acceptable materials include ASTM B637, UNS N0718, Inconel 7118 for spring components. Seats shall be pressure energized and capable of automatic cavity pressure relief unless specified otherwise. Valves with anti-blowout stems must have clear mechanical retention independent of the packing gland or actuator mounting. For ball valves in gas service and pressure classes 900 and above, a grease injection point shall be provided for the lower trunnion in 2-inch and 3-inch valves, and on both upper and lower trunnions for 4-inch and larger sizes. Ball valves intended for use in high pressure or sour service shall have welded overlay of CRA, e.g. Inconel 625, on all wetted surfaces of carbon steel components, including ball faces, stem seals, and seat pockets, to resist corrosion from trapped moisture and aggressive media. All ball valves shall be equipped with external position indicators clearly showing the open or closed state of the valve. Lever-operated valves must incorporate mechanical stops at the fully open and fully closed positions. Levers shall not exceed 450 millimeters in length unless otherwise justified, and gear-operated valves must meet ergonomic and space constraints, including adherence to insulation thicknesses. Anti-static devices are mandatory for all ball valves to discharge accumulated static electricity during operation. The valve must ensure continuous electrical continuity between the ball, stem, and body. Additionally, all valves intended for fugitive emissions critical services must be fitted with approved low-emission packing systems and meet leakage Class A as per ISO 15848-1 or equivalent. Vendor must provide prototype and, where applicable, production testing documentation to confirm compliance. General specification for valves, Part 6.6. Gate, globe, and check valves. Gate, globe, and check valves used in oil and gas facilities must be designed for high-integrity sealing, long-term durability, and safe operation across a wide range of pressure classes and service conditions. These valves must comply with internationally accepted manufacturing and testing standards, including API 600 for gate valves, BS 1873 for globe valves, and API 594 or BS 1868 for check valves. Dimensions, wall thickness, and pressure ratings must meet or exceed the criteria set out in ASME B16.34, and all face-to-face dimensions shall conform to ASME B16.10. Gate valves must be of solid wedge or parallel slide type as specified, and be provided with a backseat feature to allow replacement of gland packing while the valve is in the fully open position. Welded fabrication of gates is not permitted. The gate component shall be either forged or cast as a single piece, ensuring uniform mechanical strength and leak-tight performance. Globe valves shall use guided plug-type discs for all Class 600 and above, or for sizes 4-inch and larger, to ensure accurate seating and stability under pressure. All globe and gate valves shall include hand-wheel-operated mechanisms sized for operator safety and mechanical advantage. Hand-wheel diameters shall not exceed the valve face-to-face or end-to-end dimensions or specified limits. 800 millimeters for BS 1873 and ISO 1434 designs, 300 millimeters for BS 5154 valves, and 300 millimeters for ISO 15761 valves. Where torque requirements exceed manual effort limits, gear operators shall be provided and must include position indicators and weatherproof housings. Check valves shall be designed to function effectively in both horizontal and vertical upward flow positions. Only solid lug or double-flanged wafer check valves are acceptable. Wafer-type designs without structural rigidity shall not be permitted. Swing-type check valves are preferred unless axial flow or dual-plate designs are specifically required in the material requisition. All check valves must close reliably under low back pressure to prevent backflow and must be equipped with cushion closure features to reduce water hammer where needed. All gate valves of through conduit design shall include a double block and bleed configuration and be fitted with stem sealant injection ports. These ports shall have integral non-return valves and be capable of accommodating giant button head grease fittings. Sealant injection must be possible under full operating pressure without compromising valve integrity. This feature is especially critical for critical isolation points in process lines. Seats for 2-inch and larger gate, globe, and check valves must be of the renewable type. When renewable seats are not feasible due to design constraints, valve seating surfaces must be hard-faced using Stellite or Carbide-based coatings. Mating closure elements must be of different hardness to prevent galling. All welding of seat surfaces must follow qualified weld procedures, and test certificates must verify coating thickness, hardness, and adherence. For valves in sour or aggressive services, all pressure-containing parts must be manufactured from materials compatible with the intended media, including resistance to sulfide stress cracking and hydrogen-induced cracking. Materials must be verified through positive material identification, PMI, and certified in accordance with applicable ANACE East standards. Austenitic and duplex stainless steel components must be solution annealed and quenched as per their respective ASTM specifications. Anti-blowout stem designs are mandatory for all gate and globe valves. The stem must be mechanically retained within the valve body, independent of the gland or packing assembly. This ensures operator safety in the event of gland failure. All valves must be equipped to accept locking devices for securing the valve in either open or closed positions, and this feature shall be suitable for heavy-duty padlock installation. Each valve must be clearly marked with directional flow indicators, pressure class, size, and material identification. For all critical process applications, the vendor shall provide full documentation including valve drawings with exploded views, part numbers, material traceability records, and test results. These valves must pass hydrostatic and seat leakage testing per API 598, and additional fugitive emissions or fire testing may be required based on service classification and buyer specifications. General specification for valves, Part 7. Butterfly valves. Butterfly valves used in oil and gas facilities shall be of heavy-duty industrial design, suitable for tight shutoff service and capable of operating reliably under a wide range of pressure and temperature conditions. All butterfly valves must be bidirectional in sealing performance unless otherwise specified, and shall be designed and manufactured in accordance with API 609, ISO 5752, and ASME B16.34. Flanged ends shall comply with ASME B16.5 up to NPS 24 and ASME B16.47 Series A for NPS 26 and above. Body and disc materials must be selected based on pressure class, fluid type, and environmental exposure. The valve disc shall provide a full unobstructed bore to minimize pressure drop and must be capable of full 90-degree rotation from open to closed position. The design must prevent over travel in either direction using mechanical stops. For critical services in class 300 and above, high-performance double offset or triple offset butterfly valves are preferred. These valves must offer metal-to-metal seating and verified fire-safe design, meeting the performance criteria of API 607 or ISO 10497. For resilient seated butterfly valves, the seat material shall be compatible with hydrocarbons, water, and chemical agents commonly encountered in oil and gas processing. Seats must be field replaceable, securely retained, and resistant to compression set and extrusion. The design shall allow seat replacement without disassembling the valve body from the pipeline. In services involving amines, H2S, or high temperatures, reinforced PTFE or metal seat configurations are required. All butterfly valves must incorporate self-centering discs with low-friction bearings or bushings to support consistent torque and prevent galling during actuation. Disc and shaft assemblies shall be pinned or integrally cast to avoid slippage under torque. The shaft shall be anti-blowout in design and constructed from corrosion-resistant alloys suitable for the full pressure and temperature range of the valve. For sour service, materials must conform to applicable corrosion control standards and certifications. Actuation systems for butterfly valves shall be designed for full range and repeatability. Manually operated valves up to a defined size shall be provided with lever handles, and those exceeding torque limits or size thresholds shall include gear operators with position indicators. Lever handles must not exceed 5 times the face-to-face length for wafer, lug, or single-flange designs, and 2 times for double-flanged valves. Gear operators shall be self-locking, enclosed, and lubricated, suitable for outdoor or hazardous environments. Where valves are to be installed in insulated piping systems, extended stems or gear assemblies shall be provided so that the hand wheel or lever remains accessible. The supplier shall state the maximum insulation thickness permissible without interfering with actuation. For actuated butterfly valves, compatibility with electric, pneumatic, or hydraulic actuators must be ensured by provision of ISO 52111 TopWorks and clearly documented mounting dimensions. All valves used for shutoff in hydrocarbon services must achieve tight shutoff performance to leakage rate Class 6 per ANSI FCI 70-2 or its equivalent. Seat leakage testing must be conducted under both ambient and high-temperature conditions. For high-pressure throttling service, butterfly valves must demonstrate stable control characteristics and be suitable for modulating duty where specified in the data sheets. High-performance butterfly valves used for block applications in hydrocarbon liquid or gas service, class 150 to 600 and above, shall be fire-safe, double offset, and designed with integral body lugs of equal thickness to the valve body. These valves must be subjected to qualification testing, including torque to failure, fire testing, and fugitive emission testing where required. The manufacturer shall provide certificates of compliance, test reports, and traceable documentation for each tested unit. Triple offset butterfly valves, where used, must adhere to defined specifications for zero leakage performance and extended cycle life. The seating surfaces must be hard-faced, e.g. Stellite or Tungsten Carbide, and paired with matching or dissimilar hardness to prevent wear and galling. Disc geometry must support continuous sealing over the full pressure range, and shaft seal design must support low emission performance, explosive decompression resistance, and integrity in high cycle applications. General specification for valves, double block and bleed valves. Double block and bleed DBB valves used in oil and gas applications must provide verifiable isolation for critical process lines, ensuring personnel safety, process integrity, and ease of maintenance. These valves shall offer two independent seating surfaces that isolate process flow from both upstream and downstream directions, with a bleed port located between the seats to confirm zero leakage. All DBB valves must be designed in accordance with applicable ASME B1634 pressure temperature ratings and meet dimensional requirements defined in ASME B16.10 and B16.5/B16.47 for flanged connections. Integral DBB valve assemblies shall consist of two block valves, typically ball type, and a central bleed valve, typically needle type, packaged in a compact monolithic body to minimize potential leak paths. These assemblies shall be manufactured in compliance with internationally accepted standards such as API 6D, API 598, and EEMUA 182, and must be specifically rated for full differential pressure conditions. Modular or fabricated DBB assemblies using piping, fittings, and flanges are not acceptable unless otherwise approved for non-critical services. The valve body shall be forged or cast as a single unit to eliminate flanged connections between isolation and bleed sections. All pressure-retaining components must be designed to withstand full rated pressure independently. The block valves shall be trunnion-mounted ball valves or gate valves depending on service application and pressure class, while the bleed valve shall be a needle valve with fine control and tight shutoff characteristics. The bleed valve must be capable of venting or draining fluid trapped between block seats safely. For pressure and temperature classification, DBB valves must match the piping class in which they are installed, with pressure ratings based on ASME class 150 to 2500 or API ratings up to 10,000 psi. End connections shall be flanged, welded, or hub clamp type, as defined in the project datasheets. Face-to-face dimensions must conform to API 6D unless specifically designed as short pattern compact DBB units, which must still maintain full internal clearances and bore diameter integrity. Sealing performance is a primary requirement for DBB valves. Seat tightness must be verified through hydrostatic and high-pressure pneumatic testing as per API 598, with additional zero leakage verification for both upstream and downstream seals. The central bleed port must allow pressure monitoring or fluid sampling and may also be configured to accept permanent instrumentation, test points, or flushing connections depending on the process requirement. All DBB valves must be provided with anti-blowout stems, anti-static grounding features, and position indicators for the block valves. Where quarter-turn actuation is used, gear operators shall be included for sizes and pressures exceeding manual effort thresholds. Gearboxes must be fully enclosed, weatherproof, self-locking, and factory lubricated for field use. For automated systems, actuator-ready ISO 5211 flanges shall be provided on block valve topworks to enable field retrofit of electric or pneumatic actuators. Materials of construction for DBB valves must be suitable for the process media, including sour, abrasive, or corrosive fluids. Carbon steel bodies may be accepted where permitted, but must include CRA weld overlays, e.g. Inconel 625 or UNS NO 6625, on all wetted and sealing surfaces. For sour service, all wetted parts must comply with NACE MR 0175 ISO 15156. Non-metallic seals must be resistant to explosive decompression and chemical attack, and test data for O-rings, lip seals, or seats shall be submitted for review. Bleed ports shall be configured to facilitate safe venting and must be supplied with threaded caps, locking devices, or blanking plugs as standard. The bleed valve shall be protected from inadvertent operation using locking levers or integral design safeguards. Where space constraints exist, vendors must offer compact DBB designs with multi-port manifolds and minimal footprint, ensuring maintainability and pressure integrity are not compromised. Documentation shall include detailed cross-sectional drawings, material traceability, seat and shell test reports, and valve configuration breakdown. The supplier must clearly define the isolation philosophy used, true DBB versus double isolation and bleed, DIB, and confirm compliance with client isolation standards. Proper marking of flow direction, pressure class, and port designation must be applied on the valve body or identification plate to aid field installation and inspection.